So this is the schedule for today. First, I'm going to go over brief introductions, public relations. Then Jethrine will talk, and then we'll have a Q&A session and a brief poll at the end. So just for some of you that may not be as familiar with the ACS or the American Chemical Society, it's the largest scientific community. As members, you do have access to career development and networking resources. You can get involved in member groups. You can attend conferences and events, and also you do have access to funding and various awards. Some of the career development resources that are available are the Chemical and Engineering News Chemical and Engineering News Jobs database. If you're looking for a job and you're interested in job in the chemical sciences, that's a great place to go to find jobs. There's also the ACS does offer free career consulting. Even if you're not a member, you can still take advantage of that. They do have career pathways workshops if you're still deciding which career path is best for you, either academia, industry, government, even non-traditional type of careers. That's a great resource to take advantage of. They do have something called Chem IDP, which is individual development plans. So if you're interested in really leverage a resource that can help you to map out like your IDP for the next 5 years, et cetera, that's something to take advantage of. And I just want to shout out that the ACS does offer virtual office hours, which are usually on Zoom the first Thursday of every month. And typically it's a way to connect with scientists and learn about different topics. You can even ask them questions on networking, resume, CV, anything related to career development, professional development, et cetera. They do have a really good event coming up on November 3rd, which is finding and securing an internship. I will post a link in the chat about this webinar. So feel free to take advantage of it if you're looking for internship opportunities. You can also get involved in other groups such as the Younger Chemist Committee, which I'm currently the chair of the Virginia section, other groups such as Women Chemists, Minority Affairs, etc. So what is the Younger Chemist Committee if you're not familiar? The vision is younger leaders transforming the world through chemistry. The mission is to advocate for, develop, and support rising chemists to positively impact their careers, the ACS, and the future of chemistry. So if you're interested in learning more, you can type in acsycc.org. And just if you want to learn more about the Younger Chemists Committee under the ACS. So during the pandemic, the Virginia section has been collaborating with other local sections, particularly in the Eastern US. As you can see, even in New York and North Carolina, Puerto Rico, et cetera. Just way to leverage the resources that we all have so that we can help to provide good content for younger chemists and also have a much wider reach as well. These are some of the programs we've done in the past, such as self-care and symposium, and even other webinars on networking and how to present scientific data, and et cetera. As a result of conducting the Day in the Life series over the last 2 years, we've been recognized by the National ACS with 2 awards, 2021 for best activity or program stimulating member involvement, and just recently outstanding continuing public relations or communication program of a local section. And just if you're interested in learning ways to get involved with the Younger Chemist community, you can attend YCC events at national regional meetings. You can also reach out to me as well if you'd like to get involved in the Virginia local section. And you can even apply for ACS sponsored awards. There's one that's, I believe the deadline is on November 1st. It's called the Younger Chemist Leadership Institute Award. And this is an award for younger chemists, which allows the opportunity for younger chemists to really attend like a workshop for a weekend, and you attend a lot of different sessions to help you with leadership skills. So if you're interested in applying, the link is at the bottom. I believe I'll also provide it in the chat as well, but you can find it at acsycc.org. There's also opportunities to attend conferences and events such as the national as well as regional meeting. And just to want to plug in before we get started, we do have an upcoming career panel session, which will be hosted in person at Virginia State, but we'll also have a virtual component to it as well. I'll provide the registration link in the chat, just a way to learn about research, and just you can ask questions regarding careers, and we have various members on the panel, including myself. And now I'd like to introduce our speaker for this evening, Jethrine Mugumya. Jethrine is currently my lab mate, and she's a great scientist, and she's currently a fourth-year PhD student in chemical engineering at VCU. She did her bachelor's here at VCU, and she also minored in chemistry, math, computer science, French, and she'll share today on her research on lithium-ion battery. And in her free time, she loves watching soccer, play video games, and try out different restaurants in the Richmond area. So during the presentation, we ask that if you have any questions, feel free to put those in the chat. And also, yes, we will have a Q&A session afterwards. So Jethrine, if you'd like to take it over.
Thank you, Julian. And also thank you to the YCC and ACS for having me. So let's get started. Share my screen. Okay. Do you see my screen, Julian?
Yes.
Awesome. All right. So hello, everyone. My name is Jethrine. I am currently a fourth-year doctoral student in the Chemical and Life Science Engineering program here at VCU. And so my research mainly focuses on working with cathode materials for lithium-ion batteries, hence the title, A Day in the Life of a Battery Scientist. So brief outline of my talk. So the first few slides, I'll do an introduction, where I'm from, some of my hobbies, how I started undergraduate research, then I transitioned to the graduate research, some of the daily activities, my day-to-day, some of the lessons I learned from undergraduate research all the way to graduate school, and acknowledging the people who have helped me along the way. And so I'm originally from Kampala, Uganda, and I moved to Richmond in 2013. Can you all type in the chat your best estimate how far Kampala, Uganda is from Richmond, Virginia? I will get to those answers. See the chat. Oh, there's only one. 2,000? Ah, come on, people. Then 500,000 miles? What? Okay, I'm just gonna like, oh, 1 mile. About close to 5,000. Okay, I'm just gonna jump into it. It's about, let me see, is my PowerPoint working? There we go. Oh, yeah, it's about 11,000 kilometers, 7,300 miles. So those were like saying 5,000, about close. So this is like a third of the circumference of the Earth. So 33% distance, yeah. And so some of my hobbies include playing video games. So I'm trying to finish this Assassin's Creed because there's a new one out, and I definitely want it done before the new one comes out. My other hobby is watching soccer. Paul Scholes is my favorite player. I'm a United fan. And also trying different restaurants in Richmond. So my current favorite is a Savory Grain. It's on West Broad. We have awesome burgers and pork chop as well. If you have any suggestions, you can put it in the chat. I definitely like to try out new restaurants. Okay, So introduction. Basically, I learned about chemistry in high school. I remember the first day we had that class. We learned about the different elements of the periodic table. And I was just like, yeah, I'm definitely doing this for, I don't know however long I can do this, but I definitely want to do chemistry. And so I remember all throughout high school, I just enjoyed that class. And then also it was in the back of my mind when applying to different universities here in the US. And so the two main states I was considering were Texas and Virginia. So Virginia, because I have relatives close to DC. So my parents were like, okay, if you want to go, you have to be like close to like people, so you can get acclimatized. And then Texas, because they have really good petroleum engineering programs. So around 2013, oil was discovered in Uganda. So like yeah. So they thought, okay, petroleum engineering, and then you can like come back and work there. And so I ended up actually choosing VCU because like I sent out a bunch of different applications and VCU was the one that got back first. And like throughout the whole process, they were with me. I'd send like an email at night and be like, hey, I have this question about about the application. Can you help me with this? In the morning, I would get one. Like, okay, you can do this and do this. So like the process was pretty fast. And I was like, okay, VCU. I actually joined the chemistry program first, but then I later switched to the chemical engineering program. And so as I was doing chemical engineering, I remember the professors encouraging us to check out the different research that's being carried out in the department. So the first professor I went to was mainly focused on pharmaceutical work. I remember going there, I think it was around the fall, but then like he had a lot of students in his lab. So he said the only opening he had available was during the summer. And I remember thinking, summer, that's gonna take a while. So I like, went back and I started thinking, should I wait until the summer? Should I maybe try another lab? And then it was during, I think, the spring that a graduate student came in and asked like, hey, are there any undergrads who are interested in research? And I was like, oh, okay, I should probably check this out. And that's how I met my first advisor. His name is Dr. Muslim Demir. He's currently working as an associate professor in a university in Turkey. And so the project we were working on was looking at biomass-derived carbons for as electrode materials for supercapacitors. And so the material that we were focusing on was pea protein. So currently they use carbons derived from petroleum products, and those are expensive. And so we were looking and investigating whether this material can be used as a cheaper alternative. And so my primary role in the lab was preparing this material. So basically we heat it up at high temperatures, then we activate it using potassium hydroxide. And then I would also be in charge of preparing the electrodes for the electrochemical testing. And then from that work, we were able to find that not only did the material have a high surface area, which is important for supercapacitors, but it also had a great capacitance compared to the other materials that were in literature. And so some of the things I learned from Dr. Demir was experimental work, like how to make these samples and also take notes of what your observations are. And then working with different equipment in the lab. So like this high temperature furnace, how to operate it and how to put in samples. Then also doing analysis. So you've already prepared these materials. You need to analyze them, see if the structure is what you're looking for, the performance is what you're targeting, and then also just the general research process. So starting from literature review, then going to setting up the experiments, and then analyzing these samples, both the structure and the electrochemical performance, and also basically what a supercapacitor is, how is it important, some of the applications. And it was a really, really wonderful experience. We published an article from this work. It's in the International Journal of Hydrogen Energy. This is my first co-authored paper, and I'm really grateful for the experience. So after Dr. Muslim Demir graduated, I ended up working with another mentor who was working in the lab. His name is Dr. Dylan Rodin. He's currently working at the Savannah River National Lab, and he's working with nuclear waste. And so the project that we're working on was a kind of a continuation of what my project with Dr. Demir was, which is basically, so we have this biomass-derived material that can be used as an electrode. What if we can use this electrode as the anode in a lithium-ion battery and then prepare the cathode? And so for the cathode, we were using nickel manganese cobalt oxide as the material for the cathode, and then the pea protein would be the anode, and we were trying to make this really good battery. So the target of the cathode, we were trying to reduce the cobalt content in this material because not only is cobalt expensive, but it also issues involved with mining this material. So the less that you use, the better. But we're also trying to maintain the high performance and also the cycle stability. And so some of the things I learned working with Dr. Dylan Redeem, lab etiquette. So you're not the only one using the equipment in the lab. You need to try to manage your time accordingly and use it as effectively as possible. And then also lab safety. Lab safety, lab safety. This is important. You're working with chemicals. You need to make sure you go home with with all your 10 fingers and toes and no other problems. And then also sample prep and analysis. So with Dr. Demir, I work with supercapacitors. With Dylan, I worked with lithium-ion batteries. So learning how to make a coin cell to do electrochemical testing, and then preparing this cathode material. We're using hydrothermal treatment. It's basically putting the solution in a high pressure reactor and then heating it to high temperatures. And then also a deep dive into research. So if this happens, why does it happen? What's the science behind it? If it doesn't work out, why did it not work out? And stuff like that. And then also presentation of my research work. So at the end of this project, I was able to present my work at the undergraduate research symposium, and I'm grateful for the experience. And also grad school. What is it like doing grad school research and all the facets of it? So this is just a picture of the poster I ended up presenting at the undergraduate research symposium. It was in 2017. It's still on I don't think they have it on the VC website, but yeah, this is, yeah. Okay, so this is I'm just going to do like a brief background on what supercapacitors and batteries are. So I'm going to start with okay. Supercapacitors. So what is a capacitor? Let's start with a capacitor. A capacitor is an energy storage device that stores electrical energy when you apply a voltage. And so it does this mainly through electrostatic forces. And so supercapacitors can store 10 to 100 times more than regular capacitors. The unit of measurement, like to see how good, like to measure if this capacitor is performing well or compared to all the other capacitors, we use a farad. And if we want to measure the specific capacitance, we use a farad per gram. There are two types of supercapacitors. There's the electric double layer capacitor. Oh. Okay. Electric double layer capacitor, and then there are pseudocapacitors. And so this is a brief schematic of what a supercapacitor looks like. You basically have two electrodes, one positively charged, one negatively charged. There is electrolyte, and then there is a separator. And then a battery. Battery is a device that converts chemical energy to electrical energy via electrochemical reactions. We measure the performance of a battery using capacity. So supercapacitor is capacitance, battery is capacity. And so the unit of measurement is an ampere hour. And then there are different types of batteries: lithium-ion batteries, nickel metal hydride batteries, lithium sulfur, lithium air, very many different types of batteries. The main schematic of a battery is you have an anode and a cathode, and then you have the porous separator, and then you have the medium through which the ions transfer to and from each electrode, and that is the electrolyte. And yep. And so what we have here is a Ragon plot, and it's basically a log-log plot that compares the energy density of different energy storage devices. So I'm going to focus on supercapacitors and batteries. So the supercapacitors can discharge and charge much faster than batteries, and they also can last a longer cycle. So like supercapacitors, you can go, I think, up to 10,000, whereas batteries, you can only go up to like 100 cycles. That's the main difference. But the batteries have higher energy density compared to the supercapacitors. And so my current research. So I mainly work with cathode materials of lithium-ion batteries, but what is a lithium-ion battery? A lithium-ion battery charges and produces energy by charging and discharging by transfer of lithium ions from the cathode to the anode. And so this is the charge mechanism. Basically, when you connect your phone to a charger, what happens is that the ions transfer from the cathode back to the anode. And then when you remove it from the charger and you use it, then the lithium ions travel through the electrolyte, through the separator to the cathode. And while they do so, they release electrons which travel through the open circuit and power your phone. So applications of lithium-ion batteries, there are so many applications. I'm just going to name a few. So portable electronics, so mobile phone, laptop, can also be used to power transport systems like buses and electric vehicles. And so since my research focuses on the cathode material, I'm going to focus on the chemistries involved in the cathode. And mainly, I'm going to focus on the nickel manganese cobalt oxide. So these different chemistries are normally grouped on the structure of the final metal oxide. And so this nickel manganese cobalt oxide has a layered structure. Okay, so when synthesizing this material, there are different synthesis methods. There's the co-precipitation method, which I will talk a bit more, shall talk more about. There's a hydrothermal treatment, which I previously spoke of, just basically putting solution in a reactor, and then the synthesis is done at high pressure and high temperature. There's spray pyrolysis, and then there is sodium synthesis and also solid state synthesis. And so why is co-precipitation preferred? It's cost effective. You can easily tune the composition and morphology via the different reaction parameters. So you can adjust the pH, the temperature, and then the concentration of the reactants. And then also it's easily scaled up. It's the most commonly used method in the industry. So co-precipitation, what is precipitation? This is the process of turning a soluble compound into an insoluble compound. And so co-precipitation is when two or more substances combine to form the insoluble compound. And so in this case, we are combining the nickel, cobalt, and manganese into the insoluble compound. And so, as I mentioned before, parameters that affect the synthesis, the temperature, the pH of the solution is really important, the concentration of the reactants, and then the stirring rate. If you're using a continuous stir reactor, the stirring rate affects the morphology of the final material. And so the three main reactants involved in this co-precipitation process, we have the metal ions, so the nickel, cobalt, manganese. Normally the salts we use either nitrates or sulfates, as they easily dissolve in solution. And then you have the chelating agent. So you have these three metal ions, they are all separate in solution. So to combine them, we use a chelating agent, which can either be the ammonium ion in the ammonium hydroxide or the oxalate ion in oxalic acid or ammonium oxalate. And they combine these three ions. So then when you apply the precipitating agent or pH adjuster, then when they precipitate out of solution, each particle contains the same composition of these metal ions. Not like one will have nickel, the other one will have cobalt, manganese. Now, it should all be the same in each and every particle. So the co-precipitation process. So depending on the ion you use to precipitate out, there are three main co-precipitation synthesis process. So oxalate precursor, synthesis is when you use oxalic acid or an oxalate to precipitate out the metal ions. And so each synthesis I'll talk about briefly about the benefits of using it and also the drawback. So with oxalate synthesis, the purity of the precursor, since there is no oxidation of the manganese ion. So what happens is specifically the hydroxide synthesis, if they normally synthesize this material at a high pH. So what happens is that the manganese hydroxide that precipitates out can easily oxidize. And so the final material that you get has a manganese oxide impurity. I will show you in a second how it looks like. And then the drawback of the oxalate synthesis is the low yield, because when you add lithium to this material, the CO2, C2O4 escapes as carbon dioxide gas, and it's such a big molecule. So the amount that you start with the amount that you get is much less. So let's say you start with 2 grams of this material, you add lithium to it, you do your high temperature synthesis, you get about like 0.8 grams back. That's not good. You at least need to get 1.5 or a bit more. With hydroxide, you get homogeneous cation mixing, and then also uniform particle size from the synthesis. But the drawback is the manganese easily oxidizes, as I mentioned. And then carbonate precursor, you're using the carbonate to precipitate out. So you do not have to worry about controlling the pH during synthesis. With the hydroxide precursor, it must be maintained 11 and above, and then oxalate has to be maintained at the pH of 8. But the drawback is that you have no control over the particle size distribution. And so the work that I'll be talking about, which was recently published, focuses on hydroxide co-precipitation. So normally in hydroxide co-precipitation, the three main reactants you have. You have the metal ion solution, which is mostly metal ion sulfates. The chelating agent we use is the ammonium hydroxide, but ammonium hydroxide easily volatilizes into ammonia gas, and it's very toxic. So I looked at a different method a method where you use lower concentrations of this chelating agent, and then using a theoretical model to optimize that synthesis. And so this is a schematic of the process to prepare this material for electrochemical testing. So you start with the co-precipitation. You have your metal ion solution. You have your pH adjuster, which is a sodium hydroxide. And then you have the ammonium hydroxide, which is your chelating agent. So after you get this material, you filter it, and then you dry it. So normally during synthesis, you start with a pink precipitate. But what happens is when you dry it in air, this metal hydroxide easily oxidizes, and so you get a brown precipitate. And then this impurity is removed when you treat it with lithium and do high temperature calcination. And then finally, you get this black powder, which is the lithium nickel manganese cobalt oxide, which you can then use to perform your electrochemical analysis. So when performing electrochemical analysis, you get this powder, you make a slurry, you paste it, you coat it on a current collector, which is aluminum foil. This is battery grade aluminum foil. And then you use your anode as lithium metal. And so I'll speak briefly about the theoretical model that was used. Basically, you start with equilibrium constants, and then you solve, and then you finally get an equation, a polynomial, which you can solve in MATLAB, where if you input a pH for a specific ammonia concentration, you can get a plot. Sorry, when you input different pH values for specific ammonia concentration, you can get a plot which shows you how much metal ion is still in the solution at different pH values. And so this was done for 4 different concentrations. And so the experiment was carried out for 2 of these. We carried it out at different pH values. And then for 1 round of experiments, we used different ammonia concentrations, but we maintained the same pH. And so some of the results that we got, so tap density. This is a really important variable for materials that are used in lithium-ion batteries. So tap density is basically how much you can store in a specific volume. So the higher the tap density, the better. That means you can pack more material. Like inside the lithium-ion battery, the space is so limited. So the more material you can pack in that volume, the higher the performance. And so from these different samples, we found that material that was synthesized at a pH above 11.5 had a higher tap density, or a tap density above 1, while those materials that were synthesized at a pH below 11.5 had a tap density below 1. And then also the particle size, when we did the analysis, we found that most of the particles for these samples were between 50 and 60 microns. And then we did the electron microscopic analysis using an SEM. But basically, we found that for all these samples, what happens is that when it precipitates out of solution, it initially precipitates as these small nanoparticles, nanoplates, which then agglomerate to form these secondary particles. And then we found the orientation is dependent on the orientation of these primary particles is also dependent on pH. So if it's below 11.5, it'll have the primary particles will mostly be vertically arranged, while those synthesized in a pH above 11.5 will be more horizontally arranged. And then from these samples, we selected 3 with 3 different tap densities. We lithiated the samples using this process I described earlier. And so before we did battery testing, we looked at the crystallinity of the material. And so we found that there were no impurities. So normally if the manganese hydroxide impurity was still there, it would still be between this range, but we found no impurity. And then we also looked at the peaks, the ratio of specifically the 003 peak and the 104 peak. So during addition of lithium, what can happen is, since lithium and the nickel ions have about a similar size in their radius, what can happen is that they switch during this lithiation process. And why this is bad is because when you go to perform the charge-discharge, you will have less lithium available, and hence your performance will deteriorate rapidly over time. And so we found that the ratio to know that you will have better performance is 1.2 and above. And so from all the samples we synthesized, we found that we had a ratio above 1.2. And so some of the electrochemical analysis that we did. So this first plot is basically comparing the charge-discharge capacity of the 3 samples that we selected. We found the material with the highest tap density, which is CS06, had the highest specific capacity, about 155 milliampere hours per gram. And then the material with the lowest tap density, CS08, had the lowest specific capacity. So C rate is basically how fast you charge these samples. So if you use our 0.1 C rate, you basically take 10 hours to charge and 10 hours to discharge. Whereas if you use, like, let's say a 1 C rate, then you basically take 1 hour to charge and 1 hour to discharge. And so which brings to the second plot, which is a rate capability plot. And this will help us, first of all, see how each material performs at the different C rates. But then also when we charge it back up to the lowest C rate, does it retain most of its initial specific capacity? And we found that all 3 samples retain 90% of the initial specific capacity once we charge it back up to the lowest C rate, which was good. And then the final plot looks at the cycle stability of these 3 materials. So we got these materials at a C rate of 1C. We charge it for 100 cycles. And from this data, we were able to find that all 3 samples retained 60% of the initial specific capacity after 100 cycles, which is good. And so some of the conclusions we drew from this project, we were able to demonstrate low co-precipitation of the NMC111 hydroxide using low ammonia co-precipitation. And then from the experiments conducted, we were able to assess the accuracy of the theoretical model. So for the conditions that we tried, we found that the model was more than 50% accurate. And then we were able to perform structural and electrochemical characterization of the samples. And then also found the sample CS06 had the highest specific capacity. And then all 3 materials were able to retain 60% of their initial capacity after 100 cycles. And they were also able to had more than 90% of the initial capacity after doing after charging and discharging them at different current rates, and then going back to the lowest C rate. And so currently my work is focusing on comparing the nucleation and growth process using different reactors. So before I was using a semi-batch process, but now I'm using a tubular reactor. And so basically this tubular is known as a slug flow reactor, where you have a gas segment, and then after the gas, you have a liquid segment, then gas, liquid, gas, liquid, gas. And so it's 3-phase because they have 2 phases of liquid and then 1 phase of gas. And so the 2 phases of liquid are immiscible. And so each liquid segment is a small reactor. And then this is my setup. So it's still in the preliminary stages. And so what do I do every day? And I'm as enthusiastic at the beginning of the day, every day. So some of my activities include experiments. And then if I already made material the day before, I do analysis of that material. And then I'm also currently working with an undergraduate student. Her name is Heather Allen. And so we work on these experiments, we do this analysis, and then plot the way forward. And so sometimes these experiments don't work out. So what do? I do literature review, go to the different articles or different work that's already been published, see if they had the same problems. If I can't find it in literature, then I discuss with my colleagues in the lab. So normally I discuss with Arjun Patel, Dr. Saurav Malik, and even sometimes Dr. Julian Bob. And then sometimes I prepare for meetings, condensing all the data I've accumulated and then preparing it to present in a meeting, or preparing for conferences, poster presentations, or depending on what stage of my research I have achieved, if I've gotten enough data, preparing to publish a manuscript. And finally, I am a lab safety officer. So I'm in charge of the safety of my lab mates. So making sure that lab equipment is running properly. If not, who should I contact? How should we fix it? And then also making sure we all have all the chemicals we need in stock. And then also making sure my lab mates are up to date with their safety training, because safety is really important. And then also making sure we have lab documents up to date. So the chemical hygiene plan or the operating procedures of the different equipment in the lab. And yeah, lessons learned so far. So I would encourage, I don't know, everyone to go into research. It has been such an interesting experience. I've met so many interesting people, and being able to like formulate an idea, go from like that, from having that idea, then making those samples, like watching it work, and then finally publishing it to the world, either presenting it in conferences or publishing a paper. It's a really rewarding experience. So I highly encourage people to get into research, be willing to try something different. So when I started looking for research, I was looking more towards the pharmaceutical side, and the energy storage research kind of just happened. And then ever since then, I've kind of been focused on energy storage more than, yeah. And then sometimes things don't work out. Yes, I have tried many experiments. Sometimes like over prepare, make sure it's in the right conditions, and sometimes it just doesn't work out. I like this meme from The Office, like it explains it really well. Sometimes things just fail, and yeah, it just fails. But then how you get up from that failure is also something else I've learned. Like, yeah, getting up from that failure and learning to get back up and continue on and with your original target. And then work-life boundaries. Yes, they are really important. When I'm in the lab, I just do mainly lab stuff. But when I go home, I really, really do not want to, unless it's like a super emergency, to bring any lab work with me. Because then it just like helps me decompress. And then like when I come back fresh, I can look at the idea again or like have a new idea. And then finally, acknowledgement. So my research I wouldn't be able to have like come this far without these people. And so like not all of them are there. I try to fit as many people as possible. But Dr. Dylan Rodin, my current co-advisor, Dr. Ram Gupta, my other co-advisor, Dr. Zhang, Julian Bob, my lab mate, and then Robert Rafti. He graduated this year actually in the spring, and he's working with Thermo Fisher Scientific. He helped me greatly on that work that I just presented. Arjun Patel, Dr. Caitlin Shell, and then Dr. Saurav Malik, my other lab mate as well. And then these are also my colleagues from Dr. Zhang's lab, Sunu Kim, Dr. Mingyao Moore, she just graduated recently, and then Consuelo. I'd also like to thank the National Science Foundation and the Department of Energy for funding my work. And these are my responses. And yeah, thank you so much.